Hey guys, let's do another Coulomb's law problem. Three charges with Q equals positive 7.6 times 10 to the minus 6 coulombs are located as shown below, with L is equal to 26 centimeters. Determine the magnitude and direction of the total electric force on the bottom particle below. So we've got our three charges with the same sign, same magnitude of charge, right here on this XY coordinate system. And we are asked to find the direction and magnitude of the total electric force on Q3 here. So the best thing to do with a problem like this is to draw another picture. Drawing it on top of this will make it a bit too cluttered, so let's make something a little bit simpler to look at. Okay, so we've got our three charges. Just remember the symmetry from the original setup here. We're curious on the total electric force here on the bottom charge 3. Now, because they all have the same sign, positive, they're all going to repel. So for charge number 3, it's going to feel a repulsive force due to charge number 2 going in this direction, right? So in line with the straight line connecting 2 and 3. And so we can call that Fe for the electric force of 2 on 3. And it's also going to feel a repulsive force from charge 1. Same thing, directly in line with the straight line connecting charges 1 and 3. And it's going to go something like this. This is going to be the electric force of 1 on 3. Okay, so in the case like this, when you do problems like this, the gravitational force is negligible, okay? And again, because all the charges are the same magnitude, same sign, we're going to experience a repulsive force here at Q3. So because our charges are going off at different angles, what we want to do is establish a coordinate system like we have up here. Okay, so in the picture, we've actually got positive y going up, positive x going to the right, which is fine, but just looking at the picture, I can already see that the y components are going to be going down. So instead of dealing with negative numbers, I'm actually going to establish my own coordinate system where x is going to go to the right. So that's the same, but I'm going to have positive y going down. And that's just so that I don't have to deal with a whole bunch of negative numbers. So now let's take our electric forces and divide them up into their components. So for Fe 1 on 3, here is the vertical y component and here is the x component. So the y component vector is going to go down. The x component vector is going to go towards the right. And these two meet at a right angle like this. Okay, so at the bottom here, we've got Fe 1 on 3x. And this portion right here, this is going to be Fe 1 on 3y. Now we can do the same thing for Fe 2 on 3. We can make its y component, which is actually going to be the same space and the same position as 1 on 3y, and we can make the x component as well. So here we actually have the y component for 2 on 3 as well, so Fe 2 on 3y, and over here we've got Fe 2 on 3x. So something that should become clear to you from the beginning is that Fe 2 on 3x and Fe 1 on 3x, they're going in opposite directions. And because they're at the same angle, judging by the fact that 2 and 1 are the same distance from charge number 3, these two angles are the same. The magnitude of the charges are the same, therefore the components will be the same as well. And because they're going in opposite directions, they're going to cancel each other out. Therefore, the only components we're going to be interested in are the y components. These two y components that are going down. And we have to add those two up together and figure out the resultant based on that. Okay? So based on what I just described, we can come up with an expression to determine the total electric force on 3. So Fe3 is going to be equal to Fe 2 on 3y plus Fe 1 on 3y. Now the beauty of a problem like this, there's so much symmetry. We can see that whether it's 2 on 3 or 1 on 3, these two have the same magnitude. And so instead of adding two separate forces together, you simply can look at this as doubling one of the forces because it's the same magnitude, same distance, okay? And so what we'll do is we'll just do 2 times Fe 2 on 3y, but it really doesn't matter which one you choose, okay? So 2 times this force. Now there's a couple things to keep in mind. First, you're coming up with an expression for the electric force. Next, you're going to come up with something to adjust for the fact that it's the y component. Okay, so we have 2 times that goes in the front. Now electric force is K Q2 Q3 over R23 squared Okay, R23 is the distance between charge 2 and 3. So this takes care of FE2 on 3. Now, how do you take care of the y component? So what we have here is the expression just for this vector right here. Now, to get the y component, you see you've got the theta here. The y component is adjacent to the angle theta. Therefore, we must multiply by the cosine of the angle theta to get the y component. Okay, now we're given the charges. Q2 and Q3 are the same. They're actually just equal to Q. So Q2 equals Q3, which is just Q. So this essentially becomes Q squared. The distance R23, well, that's here. I'll draw it on this picture. R23 is just this distance right here. And we figure that out by recognizing that we have a right angle triangle here with the two shortest sides being L and L. But we have to find the hypotenuse. Okay, so we can say that R23 squared is equal to L squared plus L squared. C squared equals A squared plus B squared. Okay, so L squared plus L squared becomes 2L squared. And we're told what L is in the question. L is 26 centimeters. So 2 times 0.26 meters squared. And when you punch that in your calculator, you're going to get that R23 squared is equal to 0.1352 meters squared. Now, usually we square root that and solve for it, but I'm not even going to bother doing that extra step because I'm looking for R23 squared here. So I'm just going to go ahead and plug that value into the denominator. Okay, so at this point, we want to plug in our number. So let me continue this on down here. So 2 times, now K is your electric constant. Okay, and the value for that is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Remember, Q2 and Q3 are the same, so it's just going to be times the charge squared. 7.6 times 10 to the minus 6 coulombs squared, divided by R23 squared. We just found that. It's 0.1352 meters squared. And we can multiply that by cosine of theta. Now, to find the angle, you need to simply recognize that these two sides are the same. It doesn't matter what length they are, as long as these two sides are the same, let it be L and L, 5 centimeters and 5 centimeters, 1 million by 1 million. Doesn't matter. This angle will always come out to be 45 degrees. Okay, so therefore we're going to multiply this by the cosine of 45. And at this point, you just have to crunch this into your calculator accurately. And when you do, you are going to get an electric force on particle 3 of 5.43 newtons down. Okay, so that's it for this video, guys. If you enjoyed it, be sure to smash that like button and subscribe to Physics in the Flesh so that you catch my new videos, which I post every weekday at 12 noon. Stay tuned tomorrow at 12 noon for video 154, Coulomb's Law 5. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Woo-hoo! Holy crap, my nose looks big on camera. I gotta find a new angle.